Welcome to this lecture on BJT as an amplifier. We've studied BJT as a switch where it's fully closed or open. Yeah, we're going to kind of look at that in-between range where it's kind of throttled a little bit. It's not quite open and it's not quite closed, and unpack all of the math and the theory and stuff of how we can actually do that and control it accurately. Yeah. This video lecture will be kind of in 5 parts. This is part 1, and the other parts will actually have headings. Yeah, it'll be like a flashed heading, like a big white screen with some words on it, so that you can kind of scan through as you're going through YouTube to be able to jump into a second part or a third or a fifth part, wherever you want to go back to and restudy this lecture. So with that, right now I just want to talk about kind of 2 main things, kind of 2 themes about what we're looking at BJT as an amplifier, and then we'll just jump into applications. And those are BJT as an amplifier where we're actually amplifying voltage. And then another is BJT as an amplifier where we're amplifying current. So the 2 examples are kind of like this. One is BJT as an amplifier for voltage. So the voltage amplification is like this. If we were to study kind of what's going out there, depending on what goes in here, so we can actually put a changing voltage in here, which would actually create a changing current. And BJTs are all about actually seeing how much current's coming in and then putting an output out. So that output actually could either be voltage, or we're studying actually the collector voltage. Yeah. Or the other is that we can actually put the load right there. I could turn that into a motor and actually control the current going through the motor. So depending on what's going over here, depending on the nature of the change of something going over here, and what we're going to do as control guys, as electromechanical engineering control guys, we're actually going to put sensors on this side. And depending on the state of the sensor, we're going to have an output actually change its properties. And the output could be 2 things. One is voltage, or we can actually put the output right there, like actually a motor there, and our input actually could be driving the speed of the motor and varying the speed of the motor. So the input may be a force transducer, which we'll put over here, and that'll be the input going in there. It control the actual motor, that's actually the speed of the motor depending on the amount of force. And the other is that maybe this force transducer is actually giving us a different voltage out. And in that case, we're actually designing a sensor. And maybe that sensor is then going to hook up to some other kind of controller. So let's continue. Applications. Essentially, we can put this into 2 categories. One is, AC, and the other is DC. Yeah, amplifying AC signals and amplifying DC signals. Essentially, with control guys, we're going to focus on amplifying signals from sensors. Now, I'm going to touch lightly on AC, but really, we don't really need to delve into AC so much because we don't have sensors that are AC. I mean, we kind of do. Take a look at this. So essentially, that is a sensor that's actually a microphone, okay? I think that stands to reason. So you have a microphone as a sensor, and then that's amplifying a speaker. And that's actually a Class A amplifier. We're not actually going to delve into amplifying AC, but I wanted to show you that example. The other is this, which is pretty much kind of the same, except in this case, we're using amplifier as a sensor for vibration. There are so many different very cool sensors that sense vibration, but you can actually use a speaker as well to sense vibration. So that's the kind of the one category, that's the AC category, and again, we're not going to delve into that, and as you can see, that's kind of a little bit of a complicated circuit. We're going to get a little bit more basic, and we're going to go into, which is nice, into DC amplification. So DC sensors look like this, and we are going to have 2 categories in DC sensors. One is where we take a sensor like this, which is a force transducer, and we're actually controlling the current going through that motor. Yeah, so we're amplifying current. Or we can actually amplify voltage. So in that case, the circuit looks a little different, but really it operates in the same way. In this case, we're not amplifying current, we're amplifying voltage, and that we're really taking that voltage and we're putting it into some other kind of controller that's actually going to make some decisions on that. But the force transducer itself, it's actually just a variable resistor. And how do we turn that into voltage to go out into a controller? Or how do we actually take variable resistance and amplify that and turn that into controlling the speed of the motor, the current that goes through a motor? The other option is here, to take a look at a temperature transducer, or more specifically a thermistor. Again, it's a thing that takes temperature and it varies resistance. Yeah, that's a symbol for a thermistor. And as you can see in this case, we're just, again, controlling the motor. So this is an application where we're using a BJT to amplify a signal coming from a sensor, and we're controlling the current going through a motor. This application is the same thing. We're using the same sensor, but we're actually just controlling the output. And that voltage, that output voltage, is going into some kind of controller that's going to be making decisions about it. So those are applications. Essentially, as far as sensors go, well, it goes huge. We've got thermistors, temperature transducers. We've got thermocouples. Yeah, those are temperature transducers as well. We've got angle sensors. Actually, we can use a potentiometer as an angle sensor. Very cool application. We can also take a pressure transducer and turn that into a sensor as well. There are lots of different kinds of transducers that actually we can take the signal from and amplify and turn into a sensor. Yeah, a sensor actually is kind of a calibrated transducer in a circuit through an amplifier of some type that's actually putting an output signal in that's been calibrated and quite specific. So that's a sensor, but really we're going to focus on taking transducers that give us signals. They translate an actual event into an electrical impulse. And we're going to take that and we're going to say, well, let's amplify that and either control current with the BJT or control voltage out. Now I want to look at the theory and actually delve into how these things work and what's actually going on in here when we use them as amplifiers. Alright, so what we're going to do is unpack how a BJT works in active mode. Yeah, when it's in amplification mode. So I have an example here. We've got a piezo buzzer and then we've got a variable DC power supply for our bass. And I really want to kind of change that around and tweak it and watch what's going on here. What we're actually going to watch is this. We're going to watch what's going on between this junction, that NP junction, and this junction, that PN junction. So really, what we're looking at is the biasing of this and the biasing of that. And you know from this chart that we've got these three zones. And those three zones are the cutoff and the saturated. We've talked about those. We understand that the saturated is when it's fully closed. That in between, yeah, is where this junction right there, that NP junction, is no longer forward biased, it's reverse biased. And we'll find out how that is and what's going on, but you'll see that in action when we actually study the numbers. So that's how you identify if a BJT is in active mode. Okay, so as far as the amplification goes, what I'm going to do is I'm going to vary this, and we'll actually see how the voltage here being varied is actually seen through the current going through the buzzer. So this example is a current amplifier. Alright, so let's just delve in and look at some numbers. So what we're going to do is we're going to study the current that's actually going through our load, and then using our gain, we're going to decide what kind of resistor we need in there to fully saturate that. We're going to start with that. And then actually we're going to kind of go from there into that active region, but we're going to start with the saturation region. So if I want to know the current going through here, what I'm going to do is I'm going to say, well, I made this easy, 12.2 minus 0.2 volts. Now, why am I using 0.2 volts? And that, in this case, it's not just RC anymore, although it is, but it's actually for the buzzer, so I will label it buzzer. Now, I'm going to put this value down here, 3 kilo ohms. Now, why am I doing 0.2? Well, because it's saturated. Yeah, when this thing is fully closed, we know the voltage drop across there is 0.2. So that's what I'm putting in there because I'm starting with saturation. Okay, good. So here I've got 4 milliamps. So if I wanted to find out now how much current I needed to go through here with a gain of 100 so that 4 milliamps would go through here, this is what I'm going to do. Okay, we know that my IB is going to be my IC divided by my B. And in that case, it's 40 microamps. I think that just is standard and it makes sense. Okay, so we know I got 40 microamps. Okay, I'm going to get rid of that. I'm going to label my IB up here. 40 microamps. Okay, so now I want to choose this resistor. So if I needed 40 microamps, what resistance would be there if this was 10 volts? But you know what? Because I kind of want to play with this, I'm going to turn that and set it to 5 volts. So, with that said and done, the way I solve this is this. RB is going to be VBB minus VBE divided by IB. Okay? So, it's just Ohm's law. And we know that when it's fully saturated, this is forward biased, so therefore it's 0.7 volts. So that's easy. I'm going to write 5 minus 0.7 volts divided by 40 microamps, and that equals 107.5 kilo ohms. Okay, 107.5 kilo ohms. All right. So if I put a 107.5 kilo ohm resistor there, I would have exactly, and I set this to 5, I would have exactly 40 microamps going through there, and I know my gain is 100, so therefore I would have 4 milliamps going through here, and this buzzer would run. Okay, that's fine. So what I'm going to do is, I'm actually going to turn this up. Let's turn that up to 7 volts. If I turn it up to 7 volts, my question is, will the buzzer get louder? Okay, with 7 volts, I have to calculate how much current I have now going through. So I've got more current than that, obviously, so I've kicked the voltage up. So just going back to Ohm's law again, IB equals VBB minus VBE divided by RB. And in that case, I'm going to write 7 minus 0.7 volts divided by 107.5 kilo ohms. Now, I know that's still 0.7. It's going to still be 0.7 because this is actually fully saturated and it's forward biased. Actually, for this to go below 0.7, the voltage here would have to go really low. Okay, so now the answer there is 58.6 microamps. Okay, so will the buzzer get any louder? Well, actually, no. The reason is because this guy is actually fully saturated. I'm putting more current through here, so now that's gone up to 59 microamps. So there's more current going through here. Does it actually make this buzzer anymore? Does it make the current going through here increase? Well, the answer is no, because the switch is closed. Yeah, we're fully closing it. It's kind of like actually taking this resistor and putting if I put like a 50K, it would increase the current going through here. And that's okay. It's still closed. It just closes more. Or at least it's fully closed. It's ensured that it's closed. So increasing the voltage to 0.7 doesn't do anything. Now, what we're going to do is we're going to decrease the voltage from 5, where we saw that it did saturate, down to 4. And then we'll see what happens. Okay, now that we have 4 volts here, let's see what's going on here. Let's see how that affects what's happening with the buzzer. Right, to do that, I'm going to go back to find out how much current is going to be produced if I put 4 volts there. And that's my formula. I'm going to write down here 4 minus 0.7 volts divided by my RB, which is 107.5 kilo ohms. And in this case, I'm actually getting 30.7 microamps. Now before we had 40, which fully saturated it, so we can say that actually, do you know what, we have less current, so this guy is not fully saturated anymore. Let's look kind of forward. Let's look through the transistor using my gain to find out actually how much current is going through here now. Has it changed? Actually, it has, because this guy is closed a little bit. It's no longer fully closed. It's actually opened a little bit. Yeah, so that the switch itself isn't allowing the full current to go through. And actually, we're going to see that there's a voltage drop across CE that's greater than 0.2. Okay, check this out. To calculate that, all I do is I take my standard formula, which is my IC equals my IB times beta, and then I'm going to throw my numbers in. My IB is 30.6 microamps times 100, which is 3.06 milliamps. I'm just going to go with 3 milliamps. Okay, good. So now I've got 3 milliamps going through here. Before I had 4 milliamps. Let's get rid of that. Now, with 3 milliamps going through here, I actually want to calculate the voltage drop across this to see how much is left there. I actually want to study. I want to know what my VC is. I want to know the voltage there. So I'm just going to go back to this formula over here that you guys may remember, and that's my VC equals my VCC minus my IC times my RC. And in this case, my RC is my buzzer. Okay, so now that's just Kirchhoff's voltage law. Okay, here we go. So in this case, it's 12.2 volts minus 3 milliamps times 3 kilo ohms, and in this case that equals 2.99, or let's just go for 3 volts. Okay, so my VC is 3 volts. So that means that this junction right here, there's a voltage drop here of 3 volts. So now let's take a look at that biasing. Remember I said we're going to really study the biasing going on here. So right now I've got 3 volts potential right here, and I've got 0.7 volts potential right there. That junction is reversed bias. So we know this is in amplification or active mode. Yeah, so it's actually amplifying. So now if I were to crank this down to say like 2 volts, we would see less current going through here because I've got less current going through here, and my gain is going to be amplifying that by 100 over here, and then when I do this math again, I'm going to see that this actually gets higher. So, but it's still in reverse biased. So it's still in active mode. So as I decrease that, it's still inactive, and I see that, you know, if I kick it up to 5 volts, it becomes saturated. So there's that sweet range where we're actually amplifying this. So let's actually go on and take another look at this same example. As opposed to a current amplifier, a voltage amplifier. Okay, voltage amplifier, essentially what we've got is the same circuit, except I'm actually not putting my load here. I'm actually not going to run a load with a voltage amplifier. I'm going to use this voltage to go out to another control circuit. So I've just actually put a resistor in there that has the same value, 3 kilo ohms, and I kick this up to 10, and we'll actually see what's going on here, what kind of voltage is happening. Now, we know that if I had 5 volts here, I would actually have 40 microamps going through here. This would be fully saturated or closed, and we know that the voltage drop across a fully saturated or closed BJT here, this guy here, is 0.2 volts. So if we take a look at 0.2 volts, we say that, well, what's the voltage here? It's going to also be 0.2 volts. The voltage out is going to be 0.2 volts. So if I were to kick this up to 10, well, it wouldn't change. It's fully closed. It's still closed, so it's still going to be 0.2 volts. All right. So now I'm going to kick this down to 4 volts. If I kick that down to 4 volts, we know that the current going through here is going to be 30 milliamps. And we did that because before we calculated 30 microamps going through here, so sorry, 3 milliamps. So with 30 microamps going through here, I'm going to have 3 milliamps going through here. So with 3 milliamps going through here, I know that this is going to be 3 milliamps. So my IC is 3 milliamps. Okay. Again, I want to know what my voltage out's going to be. Now my voltage out is actually equal to my VC. So what I'm going to do is actually use that same formula, and just rewrite it a little bit. I'm going to say my VC, for now, I'm going to go back to the formula, is my VCC minus my IC times my RC. And from there, I know that this guy is actually out, because my VC is the same as my V out. So I want to study that. Here we go. 12.2 volts minus 3 milliamps times 3 kilo ohms. And in that case, my voltage is going to be, again, 3 volts. So my V out is 3 volts. Now, the current going through here is lower, and that's fine. That's not my load. I don't really care about the current going through there. I want to know what my voltage out here is. So actually, if I put 4 volts in here, I get 3 volts out here. Let's see what happens if I kick this down to like 1 volt. Okay, 1 volt there. What's happening here? Well, I've got to find out how much current's going through here so I can calculate that. To figure out how much current is going through here, I need to know how much current's going through here so I can apply it to this to find out. So with that, I'm going to say my IB, going back to Ohm's law, IB is my VCC minus my VCE divided by my RB. We know that's 0.2 volts. So I'm going to do 0.7 volts. 0.7 volts divided by 107.5 kilo ohms, and that is going to be 2.8 microamps. 2.8 microamps. Okay, so now what's the current going through here? That's easy. My IC is going to be my IB times my B, and that is then going to be it's going to actually be 280 microamps. Yeah, less than a milliamp. Okay, cool. So now, that's pretty small. What's my V out going to be? Well, I have to then go through this same process over here, but I'm just going to put some different values in here. I'm just going to do 280 microamps times 3 kilo ohms, and in that case, it's a lot higher. 11.36. 11.36 volts. So, as this gets lower and lower, that's going to get higher and higher. Okay. So, as I adjust this, I could be imagining that was actually a sensor that's changing its value. So, we've looked at current and we've looked at voltage amplification, and we understand that in all cases, when we're in amplification mode, this guy is in reverse bias and that guy is in forward bias. Okay, so let's actually take a look at what this looks like with sensors and stuff. Let's go into some actual examples. Okay, hold on to your hat. This is going to be good. Yeah, this is going to get pretty heavy, okay? So we're going to look at two BJTs as amplifiers, examples. One is we're going to make a sensor. Yeah, we're going to take a thermistor and make a sensor with it. Yeah, we're going to take a thermistor, which is a really cool resistive resistor, which is essentially a transducer. Transduces temperature into resistance, and then we're going to take that and turn it into a sensor. We're going to have voltage coming out. Okay, good. The other example we're going to use is we're actually going to use a kind of a potentiometer, also kind of as a transducer and make a sensor to some degree. Actually, we're going to use a potentiometer to control the speed of a motor by just turning it. And maybe we can even say that that potentiometer is a angle sensor. We could do that. So two things we're going to touch on to. So right now, let's talk about how to put a thermistor into here to actually have variable resistance, give us a very specific voltage coming out of here. All right. So we've got this kind of basic BJT here, and I've left this big blank here. And what I want to do is I want to align some kind of thermistor in here. I want to obviously put voltage in here, and I know that the voltage needs to change. It needs to vary because actually I want a varying output here. So I'm going to have an analog signal coming in that's going to be in relation to the changing of the temperature, and then obviously the voltage coming out. I looked at 3 of these. Yeah, check these out. So this is the first thermistor that I looked at, which was pretty cool. It looks kind of like a Zener diode. Yeah, so that can go into a box or wherever you need to, or whatever temperature is around that thing, it will change its resistance. Cool. Now, I looked at this one as well. I kind of like that one. It looks a little bit like a capacitor. I thought maybe that's cool because you can actually kind of stick it into something. If you had some kind of box or a little hole in something, you could stick it in there almost like a probe. I like this one even better. It's more probe-like. It's designed specifically. It has a sheath on it. I like the attributes about this because it's a 50-watt probe, which is pretty cool. Sorry, I just lied to you. 50 milliwatt probe. And we'll see that in the data sheet for a second, but take a look at this. Yeah, I like this. So this chart shows us the range of temperatures that it can handle, and also the range of resistances. So it specifically tells you the resistance or typical resistance. This is kind of tunable. We have to tune it to some degree. So it shows you the specific range of resistances and the range of temperature, and it's in Celsius. Cool. So we're going to go from, say, 0 over to 170, and we're going to deal with those two resistances, and those will be our maximum and a minimum resistances. So we're going to use that one. So later we'll look at the data sheet a little bit more, but right now I actually want to get into using a voltage divider to actually put some kind of transducer in here that is going to give us a varying voltage out. Okay, good. So what I'm going to do is I'm just going to go theoretical here, real kind of, just going to go nice and sloppy here. So let's say I tied that into there. So that was 12 volts coming in there, and that was R1, and that was R2. Cool, I can't even draw an R. So if this guy was 10 kilo ohms, and that was 10 kilo ohms, right there, my VBB is going to be 6 volts. We know that because I've got 12 volts coming in and I've got 10 and 10, and that's fine. It's a voltage divider and it's evenly distributed. Now, if for some reason this resistor was changing its value and it went up to 20 kilo ohms or higher, obviously my VBB would go down. Yeah. Now, the other thing is, if I were to change this to a 1K ohm, for some reason it just changed to a 1K ohm, actually because the nature of a thermistor does that, and other things as well, force transducers and things. So, stuff changes resistance depending on the nature of what it's designed to change resistance on. And what we're doing is now we're seeing a varying voltage at VBB. So that's actually how we're going to design this. Now, we have to think about what we want to do here. Do we want to put our thermistor up here, or do we want to put it down there? Well, if we look at the data, we can see that the resistance increases as the temperature increases. Okay, so I'm assuming that if we're going to make a sensor, we're going to make it so that the voltage out of here is going to increase as the temperature increases. I kind of like that. So, how does that work? Okay, well, we know that the output, if I'm looking at BJTs and amplifiers as an output, it's a little bit backwards. And that's because if I have more current going through here, what's going to happen is that this is going to be closed. If that's closed, then the voltage out here is going to be 0, because that's just a closed switch. Or it's actually going to be 0.2, but we'll just call it 0. And if I have less current going through here, that's going to be open switch. And as this becomes open, this value gets closer and closer to that. Right. So, again, going back to where we're going to put this thing, if I put my thermistor, say, down here, and as the temperature went up, the voltage drop across here would increase, so therefore my VBB would increase, so therefore my current through here would increase, so therefore this would decrease. So what I want to do is I want to actually put my thermistor up here, and I want to have another resistor down there. So we're going to roll with this, and I'm going to put my thermistor in here. Thermistors are pretty cool. They look like this. And I got a little line going there, and that line going down, and then that goes up here. Now, our data sheet, that chart, shows us that the lowest value, we're going to go with 0, so 477, and the highest value is 1410. All right, so I'm just going to go like this. I'm going to label this RT for my thermistor, and then I'm going to say 477 ohms to 1410 ohms. We're going to work with these a lot because they're going to change everything. Essentially, everything we've done with checking BJT as a switch, we have to kind of twice because we have to do it for that value and that value. We also have to calculate voltages and stuff for that value. So the next step actually is going to be calculating this resistance here. So the actual formula for that, I kind of like this formula. This is something I've used for years. I figured it out years ago. But essentially, if I have any kind of voltage divider and I want to get the most out of it, the greatest range out of my voltage divider, use this formula. So I'm going to say R1 is going to be equal to this. So I'm going to say my R thermistor max times my R thermistor min. That is actually going to give me a value so that this range is going to give me the greatest range of VBB. So over here I've already done this, and that's 820 ohms. So, and if it comes out to some other weird number of 816.423, it doesn't matter. Just put an 820 or whatever resistor you have that's close enough. You may have an 810 in your kit. You can use that as well, but I'm just going to label it 810. So that's 820. Okay, I got my 820 ohms here. Now, we have to think about, well, what kind of resistor do I want to use here? What's going on? What kind of voltage do I want out here? Well, if I'm going to tie this into a controller, like an Arduino or a PLC or maybe a Raspberry Pi, let's just go for an Arduino. Let's say I wanted to put this into an Arduino. By the way, Arduinos or any kind of controller that's seeing voltage, it doesn't need a lot of current, or it doesn't draw a lot of current. It's designed specifically not to draw a lot of current. So if I were to hook an Arduino up to this, if I were to have this going into a pin of an Arduino, the Arduino would be just drawing like a milliamp, really small amount of current. So that's kind of actually important to know when we're choosing this. Now, essentially, I don't need much current to go through here. So the larger I make this, the better for me, because then I can make this larger, and if I make that larger, I need less current going through here, and it's all kind of better if I use less current, especially through this thing, because that thing can only handle so much current, actually. And right now, we are going to later calculate how much current is going through here so that we can see whether this can actually handle this. But let's continue back on what I'm talking about over here. We're trying to select this resistor. Okay, so what I need to do also, at some point when I put an Arduino here, I'm going to put a tie-down resistor. And that'll be like a 10K. You can use probably a 50K if you want, but it's going to be a really large number. What I want to do is I want to make this kind of at least 10 times smaller than my tie-down resistor. So if I used a minimum 10K for my tie-down resistor, I use a 1K here. So I'm going to make this 1 kilo ohm. And we're good with that. That's not going to draw very much current. No matter what this is, whatever the current going through here, if there's enough current going through here that this is saturated, then the maximum of current that this thing can draw will be drawn. And that'll be fine. Even if it's small, it's still drawing current. And then this thing will be closed, and that voltage will be either a 12 or 0.2. Again, we don't care how much current we have out of here. If I put a 1K in there, I'm definitely going to have enough current. It'll be really small, but it's fine because the Arduino doesn't need very much at all. So with that said and done, I'm going to put a 1K in there, and we'll see how that kind of translates over here. Obviously, if I have my gain, this guy is going to be whatever it is, whatever the current is going through here divided by the gain. Let's actually choose again. Let's say it's 100. Now I haven't selected a particular transistor, but let's just say the beta is 100. So I'm just going to write that up here. Okay, so my current gain is 100. So then I'm going to calculate the current going through here, and then I'm going to calculate the required current that I need to go through here to fully saturate it. And then I'm going to go back and try and figure out what resistor I need here to do that. But I kind of, again, have to go back and look at this two ways. Well, I need to calculate some stuff so that this thing fully saturates, and actually it's kind of completely off. Yeah, it goes off into cutoff range. So I have to design this resistor so that the current coming through here, depending on how the voltage changes here, depending on this resistive change, is going to be the current going through here is actually going to completely open this or completely close it. It's a balance. Okay, so to do that, what we need to do next is we actually have to figure out how much current we need to go through here using the gain to figure out how much current we have here. So that's easy. To calculate the current through here, I'm just going to go back to this formula here where I say IC equals VCC minus VCE divided by RC. Okay, so that's because it's just Ohm's law. I need the voltage drop across this, and that's what that looks like. So if I throw these numbers in here and I put 12 minus 0.2 volts divided by 1,000 ohms, I get 11.8 milliamps. So now I can calculate how much current I need to go through here to fully saturate this. So that's easy. I'm just going to do this over here. So I'm going to say my IB, but I need to use some other terms here. My IB maximum, yeah, for saturation, because I have to look at the current in kind of two situations. So my IB maximum is going to actually equal my IC, and I'm going to call that max as well,
divided by B, and in that case that is 118 microamps.
Okay, so that's my minimum. And what's the minimum here, the minimum current? Well, essentially I want this to be wide open, so my minimum current is actually going to be 0. Okay, so going with this, I know that. So now what I'm going to do is I'm going to say, all right, so let me calculate the resistor I need here, which is a pretty standard step. But the problem is, dude, I don't know what this voltage is because I don't know what this thing's set to. I mean, which of these resistors do I use? Well, what I'm doing is I'm looking at full saturation. So at full saturation, what's going on is that I want the highest voltage here. So when I want the highest voltage here, this guy is going to be at its lowest value. And that's because it's a voltage divider. And we know if that is higher than this, then the voltage is going to be higher. And if this is higher than that, the voltage is going to be lower. So what I need to do is I need to calculate what my voltage here is going to be when this thing is at 477. And then for that, I just use the voltage divider. So I've got the voltage divider formula here, and let's kind of unpack this a little bit. What I'm looking at is I want to see how these two divide up the voltage. Well, the voltage is 12 volts. I've got 12 volts coming here. So my source voltage is my VCC, and then these are the two that are dividing it. So essentially what I've done is I've written the formula here. Now specifically I'm using RT minimum, right? Because that makes sense. This has to be at its smallest for this value to be at its largest, because that's got to be bigger than that. And I'm focusing on looking at the voltage drop across my R1. So with that said and done, I put the numbers in here. Now I'm going to put 477 ohms here because I'm looking for the minimum, and that value is actually 7.59 volts. I'm going to write that over here. 7.59 volts. Now, you know, you don't have to keep these in your memory because they don't have to be like super accurate. Now, I'm on a roll here. I'm kind of doing this anyway. So what I'm going to do is I'm going to take a look at this same value, but instead I want to look at the other end of the spectrum here. So I'm going to do the maximum, which is going to give me the minimum voltage here. Okay, good. So with that said and done, that's going to be 1410 ohms, and that is 4.41 volts. Okay, I'll write that here. 4.41 volts. Now I have my maximum and my minimum values here. I'm going to calculate the current going through here now with my maximum voltage that I expect to saturate this. Yeah, so I have to choose a specific resistor here so that the maximum voltage I can get out of these is actually going to fully saturate that thing. Okay, good. So that's easy. I know that to do that, I have to do my RB is going to be equal to my VBB minus my VBE divided by IB, and IB, when in full saturation, is this guy here. So with that said and done, if I put my numbers in here, I'm going to put 7.59 minus 0.7 volts divided by 118 microamps, and that's 57.39 kilo ohms. All right, so I'm just going to roll with the 57.39 kilo ohms here. And I'm going to write that here. Now we won't get one exactly like that, but you know, you'll probably use a trimming pot and just put it in there to get it exactly that amount, because we really want this value to be that number. So I'm going to write here 57.39 kilo ohms. Now we're going to find the voltage that comes out of here when that thing is at its lowest value, and then we'll find the voltage that comes out of here when that thing's at its highest value. So remember, when that's at its lowest value, we get the highest amount of voltage here, so the highest amount of current, so that thing is fully closed. So the voltage out here actually is just going to be 0.2 volts. We've already calculated this guy, from this value here, knowing that that's going to be the maximum, and we know that the way we calculated that was we actually used this current, and that current came from this current, which is the current that's going through here. So we already know that the voltage out at this point when this guy at its lowest value, the voltage out is actually going to be 0.2 volts. We'll just call that 0. But what I'm really after is what the voltage out is going to be when this guy is at its maximum, or more specifically when the temperature's up. That's going to be my high voltage. Okay, so over here what I'm going to take a look at is I'm going to say, oh, wait a second, how much current is going through here when this thing is at its highest value? Well, I know that when that's at its highest value, the voltage coming out here is this. So what I need to now is actually, I have to calculate how much current's going through here when that's at its, when the temperature is at its highest. So that'll be a low amount of current, and this thing will be slightly open. All right. Well, to do that, all I'm going to do is actually just find out how much current's going through. I'm just going to do this. My IB is actually going to be equal to my VBB minus my VCE divided by my RB, and in that case I'm dealing with this low number, 4.41 minus 0.7 volts divided by, in this case, 57.39 kiloohms, and that value to the exponent 3, that equals 64 microamps. Okay, good. So I'm at a 64 microamps. Now, I know my gain is 100, so I'm just going to multiply that by 100. 100 equals, okay, cool. So I am going to look at, now I'm going to take this value and I'm going to calculate my IC minimum. And that is going to be my IB minimum times my gain. And in that case, the answer is 6.45 milliamps. Cool. So when the temperature is at its hottest, that guy is at its highest value. This then is at its lowest value, which is this guy. Therefore, we have less current going through here. The current going through it is that. And because my gain is 100, I know the current going through here is 6.45 milliamps. So now what I need to do is calculate what the voltage out is when this thing is kind of half open and half closed, and I have less voltage drop across this. What's the voltage out? So I've written my minimum collector current here, and now what I'm going to do is I'm going to write this formula down to find out my V out, and I'll use this formula which you recognize. That's going to be VCC minus IC RC, but more specifically that tells us the voltage here from here to here, but we're actually looking at this voltage anyway, so the V out is the same. Okay, good. So my V out, and that's going to be 12 volts minus 6.46 milliamps times 1,000 ohms, and that is 5.47 volts. 5.47 volts. Okay, so we're kind of done this, although we have a little bit more to talk about from the kind of the Arduino side. So what we've done is we've got this changing resistive transducer, and we wanted to make it so that it gives a changing voltage, and we looked at the two different voltages it can give us. We looked at how much current we needed, and then we said, okay, so if I have these two voltages here and I know my maximum voltage is going to be saturating this thing, then I have to calculate the right resistor here to fully saturate that, so that my voltage out is actually going to be 0 volts or 0.2 volts. So when this thing is actually at its minimum temperature, I'm going to get 0.2 volts out. When it's at its maximum temperature, I'm going to get 5.47 volts. Now, essentially what's going on is that an Arduino doesn't like anything more than 5 volts. Doesn't like that. So you can tweak this a bunch of different ways. One is, you can, and this is really the ultimate way to do it, you can do this. put a pot in there. Get a 1K pot and put it in there. And you can adjust that. You can see that if I made this actually to a lower value, this would come down just a little bit and you could tweak it so it just came to 5. And also, you're going to need to be doing that because that's not always going to be exactly 100. It's going to be some other value. So you're going to want to have some adjustability. Also, this guy, you might want to put a trimming pot in there as well so you can tune it to exactly what it really needs. So these two things will allow you to tune your circuit. Yeah, and that's what I was telling you before about trimming pots or potentiometers, period. They help us tune circuits. So you can tune these things so you can get exactly that. Now, I'll add one more thing before we jump on to amplification of current, and that is this. If I wanted an offset, so if I wanted, say, my voltage coming out of here to go from 3 volts to 7 volts or some other value, I'd have to change things around to actually get that up to 7 volts. But what I could do here is if I needed that offset, if I needed it to go from, say, 2 to some other number as opposed to from 0, I would do this. RE. I'd throw an RE in there. Now that's a whole other thing. You know, I just leave you with that and challenge you to kind of recalculate all of this to give yourself an offset of 2 volts. Okay, let's go on to doing all of this over again with a potentiometer control the speed of a motor. So we're going to use an amplifier amplifying current. In this case, we're amplifying voltage. Now we're going to amplify current.